what I'm going to do, here before lunch, I have myself here and then Dr. Fabian Fernandez, who both of us work on nutrient management issues. I'm going to talk more kind of conceptually on what's going on right now for best management practices for the southeastern region. And some of you, as you came in, you saw that green publication that was on the table, and that's technically the current publication, but we are in process of revising the publication. That publication actually came out about the time I started here in Minnesota. It was around 2008. And from what we've seen over the past few years, we've had a lot of, we look at a lot of research in the last 17, 18 years. And so it's time to go through and make some revisions to those publications. I'm not expecting as much of a change in terms of what you're seeing in that publication for the Southeast, though. So if you look at some of the general trends and some things that kind of went into some of these, how these BMP, the best management practice regions, are split, I'll talk a little bit about that. And if we look at the practices here, I mean, you've been doing more of the practices that have been, we start talking about practices that tend to mitigate the reduce of risk for nitrate loss to the water. I mean, it's been many of the practices that have been recommended in this region have been more of those top practices. So with our best management practices of the regions, they are regionalized, and a lot of that really reflects the differences we'll see across the state in soils and some of the climatic conditions. And I'll talk about why that is. I'll just show you kind of the main emphasis where we're looking at, particularly when it deals with nitrate, why these regions are the way they are. I mean, if you look at them, the regions are right on county lines. The thing that I will say, though, is that we do know that when we start talking about soils, is that soils don't stop at county lines. So Brad gave an example earlier talking about limestone outcrops in eastern Rice County. The main thing on these BMP regions is that you have to know is that just because you're in a region doesn't mean that the soils that you might be farming may not need to have some other considerations for one of these other regions. So I mean, I said the Southeast, I think, is a really good dividing line for this, because we have some soils that would be more like what's in the Southeast and eastern Rice County, but then you might go into western Goodhue County in the southwest portion. Some of those soils might be more similar to the South Central region. So there is some also crop focus to this if you are dealing with things like small grains. A lot of that focuses in the Northwest. That's one of the things I'm trying to get around with the updates. So I'm trying to do a few things. I'm trying to be more specific with all the crops within the regions, have a bit more of a focus on manure in some of these publications than we had within the last update, and then again, just look at some of the current research. So this just breaks things down. I mean, really the bigger question really is the coarse textured soils, because we do know there are inclusions here and there across the region. I mean, it really depends to me in terms of how large those inclusions are. If you have a field that would be an irrigated sand in one of the, say, the Southeast region, you might want to look at the coarse textured Bolton. But again, these things are meant to be soil specific, so don't get stuck on just because you're in a region. That's the publication that you're going to want to use. So why are they broken out? If we look at the state of Minnesota, if you look at we look at just simply at precipitation and climate, which I don't have up here. If you look at taking a line from the southeast to the northeast, what we tend to see in the southeast, the warmer conditions, wetter conditions, and that tends to decrease as we go northwest across the state. So a lot of that really boils into why we start making changes in terms of our nitrogen management recommendations in different areas of the state. In situations like in the southeast, particularly if we're in warmer, wetter conditions, we have a greater likelihood of a conversion to nitrate much quicker. And they start talking about shallower soils, it becomes more problematic in terms of timing and some other practices that come into play when it comes into our BMPs. And really where a lot of this boils down to is if you start looking at what we call the evapotranspiration, or what we call the leaching index, which is the relative potential to leach nutrients deeper in the profile, where we see a higher potential in the southeast. And as we go to the northwest, we see a much lower potential to move nitrate in the profile. And this is pretty easy to see if you'd ever dig down in the soil and see where the carbonate layer, because most of our soils are based on materials that were high in carbonates. And you can see that in western Minnesota, those carbonates are shallower to the surface versus in the eastern part of the state, they tend to be deeper. So if you look at annual precipitation, these are the general trends. And that's one of the reasons too, if you look at the trends over time, one of the reasons why we need to update these best management practices on a more consistent basis, just as we see changes in trends. And really in the southeastern part of Minnesota, we really see the precipitation trends being more consistent. Where it becomes more problematic when we start talking about best management practices are south central and southwestern Minnesota, where we've seen some pretty significant increases in precipitation within the last 30 years. So this is looking at precipitation versus evapotranspiration. And so again, what this boils down to, if you look at evapotranspiration, what that is, it's the evaporation of water from the soil surface coupled with the transpiration of water through the plant. So essentially, corn, soybean, they sweat. They move water through the plant, and so that's where when we start talking about peak water demand, why that occurs at points in time when we have larger plants is because there's going to be a greater demand for water to cool the plants because they don't like to be hot like most of us don't like to be hot. And so if you look at why things change in terms of, a lot of this boils down to timing of application, is really boils down to the ability of, or the relative potential of nitrate to move in deeper in the profile. And we see that potential decrease as we go from the southeastern to the northwestern corner of the state. So if we look at the southeast specifically, really it boils around a lot of the depth to the bedrock. And that's really where a lot of these practices come into play, where we know that it's just much easier for nitrate to get down deeper in the profile to points at where the roots aren't, where it can't effectively be taken up. So if we look at specifics on the southeast, really a lot of the BMPs really focus on minimizing direct movement when we start talking about of nitrate into the subsurface waters, the karst topography presenting a lot of challenges. And then we start talking about the depth of bedrock being variable within these fields. It becomes more problematic in terms of the overall nitrogen management. So when we start talking about application, really a lot of what when we start talking about this leaching index boils a lot down to why we don't recommend fall application of commercial fertilizer in the southeastern part of the state. It's because of the water solubility of it. The material is relatively high, and if we get situations where we can get conversion to nitrate, once that fertilizer is in the nitrate form, there's absolutely nothing we can do to stabilize it. So when you're talking about inhibitors or stabilizers, once it gets to a certain point, there's really nothing you can do. So here's where we're at now, and I broke this down, and I like this one because essentially it's talking about some of the general recommendations across different areas of the state. The red, I kind of color-coded these, are areas that are NR not recommended. Acceptable with risk are yellows, and I have some question marks right now, and those are the things we're looking at. And again, nothing as much in this zone in terms of the research. It's been pretty consistent with what we've been seeing. Save situations maybe with products like ESN, which is more of where I have dollar signs, are more of an economic risk versus an environmental risk for increase for loss. And then green are the recommended practices. If we look at across, this is the southeast, the south central, and the course, kind of look at consistency in split applications or pre-plant applications, typically being more of the recommended practices, except for 100% pre-plant and coarse textured soils, which we know that there's more risk because we know we have more risk for downward or more leaching of nutrients within the profile. So if you look at a lot of the practices that aren't recommended, fall application being one of them, it's again just because we have a much greater potential, if there is nitrate in the profile, for it to be lost early in the spring just because of the depth of bedrock within these regions. So it's kind of, again, the change. If you look at it, it's really more of a timing component. The rate-wise, which I'll talk about here, is we really make no distinction, and I've looked at that in different areas of the state to try to break the state out, looking at different regions for different rate recommendations, and it just hasn't been consistent. And again, I'll get to that here as we go through this presentation. So this is one of the things I want to talk about specifically, because this does come up from time to time, especially when we start talking about split applications being on that recommended side, is do we have to always have split applications in these regions? And it's one of the things that we've looked at a lot in our research, spring versus split application. What's the general benefit? Because typically, when we get into situations where we have a high potential for loss, it's a bigger difference when we start talking about switching from fall to spring. Then our data really hasn't been as consistent with a spring or a split application. So I'm not going to be up here talking to a group saying that everybody needs to split apply your nitrogen. Certainly it does reduce the risk for loss, particularly early in the growing season, but a lot of time, and again, with a lot of these practices, they're data driven. So we let the data tell us what we see in these regions, what we should be recommending just based on the information we have from current research. So really a lot of timing really boils down to whether or not you're going to get loss. And that's really where when we start looking at timing, it's if you're not going to have a high potential for loss, then timing becomes, particularly with the split application or an in-season application, becomes less important. I think there's certainly some advantages if you're looking at timing, particularly when it comes to making adjustments. But when we start looking at a lot of the data, the question is whether or not we can, one, reduce our nitrogen rate if we look at a split application, and then again, two, if we look at those reduced rates, how does that impact when it comes to some of the overall nitrogen loss? The thing about when we start talking about later applications, and I'll talk about this, is that there is an optimal time if you're looking at a planned side dress application based on a lot of our data. And our recommendation right now is to have all of our side dress, if it's a planned N application, on by about V6 or about the time that the corn is 1 foot tall. And there's a reason for that. And again, I'll get to that here as we move forward. So I like to show this data because it talks a little bit about is how much nitrogen do we need at points in time during the growing season. So obviously if we start talking about planting, you start looking at smaller plants, we know that if we start looking at nitrogen uptake, it really mirrors a lot of what we see in terms of overall plant growth. So if you think at early in the growing season, up through about V1, V2 in many cases, that they're the small amount of nitrogen that we have in the corn seed itself is likely going to be enough to carry you to that point. If you look at V6, we need roughly about 10% of our total nitrogen is taken up. And we start talking about the R3 or milk stage, at that point in time, about 80% of the N is taken up. And I'll show this in a different form here in a moment here that'll kind of visualize this better. Because it really boils down to essentially when we start talking about split applications and timing on the recommendation side is trying to match our availability of nitrogen in the soil to when the crop is going to need it the most. And again, trying to maintain forms that are going to be less likely leached out of the profile as much as possible to when we end up hitting peak demand. One thing I know that's come up in the last 10 years, and I've seen that a lot in trade publication, is talking about the 80% of your nitrogen that's taken up post-tasseling, or in this case, beyond about R3. One of the things we see in a lot of these soils is when we start talking about nitrogen, a lot of times we show the total uptake over time, and really we need to visualize this in terms of the amount that crop is demanding on a daily basis at key points in time during the growing season. And as I said, I'll get back to this because we start talking about the end of the growing season when we have a lot of mineralization occurring, that in many cases, my thoughts on a lot of this for what we've seen essentially is that those late applications really are not needed just because what we're getting out of our soils, as Brad was talking about, the amount potentially we can mineralize should be enough to maximize our yield, and that in most cases we see peak demand right around here, and that's really when the bulk of our fertilizer is important in trying to mitigate some of the deficiencies we may see because mineralization hasn't picked up at those early stages. So is it preferred, is it needed in side dress? I mean, really, again, it depends on your situation. So if you have high degree of loss, I mean, I'm sure a lot of you, if you've adopted it, you've seen benefits to it, and that's why you're actually doing it. But it isn't necessarily consistent across all locations in the state that we see that we need to be looking at side dress. Again, spring is better than fall, but we start talking about a pre-plant, it's always not much better than a side dress application. So really, it's more of a risk mitigation strategy, and it's really trying to meet your peak demand. And I think this is really the key, and it's when we start talking about nitrogen, when we start talking about all these BMPs, is looking at the flexibility of options we have, because that's really key when we start talking about management, is what options do we have, what do we know about these options in terms of how they might affect the overall nitrogen requirement and potential nitrogen losses to the plant. Putting less up front, I think we start talking about it, I mean, there are some advantages to that, and essentially that is really looking at options and flexibility to make adjustments in season. So if we start getting caught with situations where we might expect to need more or less nitrogen, we can make that decision if we haven't applied more than what that crop needs. And that's really been the challenge when we look at all of our data and all the rate data, is trying to figure out what that exact right rate is, because right now, the technology really limits us in terms of that window where we're at plus or minus that exact rate on a yearly basis. The bottom one, though, I think is important really, and we start talking about it, unless you're dealing with an irrigated situation where you can fertigate annually, the spoon feeding option really just, when we start looking at it, isn't that viable. And a lot of that really boils down to essentially, when we start talking about these peak uptake periods, is that whether or not we're shorting ourselves from this option, and it's a lot of high energy cost that it takes to do that. So unless you have that option, particularly through a center pivot, really looking at a lot of our data is showing just a single splitter, a single in-season application is really enough if you start talking about a side dress to maximize crop yields. So I'm hoping, Fabian, you aren't covering this. So this is the only of Fabian's data. I like this data because it talks a little bit about the side dress when we start talking about in-season applications and do we need it. Because again, a lot of my data, if we look at whether we're in Southeast, I've had a number of trials to the east of here at the Lawler's farm, or also over by St. Charles, where we've looked at split or a single application. In many cases, it takes the same amount of N relative whether we apply it once in the spring or whether we apply a small rate in the spring with a split application. So really what it boils down to is factoring in what is your overall N loss potential in the spring to whether or not we start looking at delayed applications being beneficial to a crop itself. So what this is looking at essentially are three conditions: higher spring N loss, so this would be a situation with more sandier soils or something that's more leakier where we'd expect to have more nitrogen loss. These are applications pre-plant, V2, V4, V6, V8, and V12, versus a situation where there's some risk for N loss, but it isn't as much as we'd consider in a sandier situation versus a dry weather condition. And this is, I think, one of the key points, and one of the things we've seen in situations is that we have to make sure if we are applying that nitrogen is that it can actually get to a point where that plant is taking it up. So we start talking about dry conditions, delaying applications, going too late. We know that there can be issues if the rain shuts off, since the bulk of our nitrogen that the plant's going to effectively use on an annual basis in the nitrate form, it's going to move with water into the plant roots as that plant's taking up water. So if it's near the surface or a situation where we aren't getting the nitrogen down deep enough, it can be there in the soil, but effectively it's not available to the crop if it can't be taken up. So delaying applications in those beyond about V4 to V6, more risk for potential yield loss. We look at the low spring N loss potential. Generally, if you can start rowing the plant, this is by about V2, V4, V6, V8, seeing similar effects or similar effects on yield where we have a pretty wide ranging window for our application. Then in sandier soils, V4, V6 being kind of the optimal time to start delaying later in the season, trying to match that uptake period for when that crop is going to need it the most. So it's not a single answer, and that's one of the things. You have to know your soils, you have to know your conditions in terms of what the general risk is. But in general, for those planting side dress, it's why we recommend really starting once you can row the corn, and most often is the optimal time, and trying to get our planned split applications beyond about V6. And if we look at later applications, we just don't see it adding an extra split into there, particularly with applications at tasseling, which has become more of an emphasis with situations like the Y-drop system, where I think it's a fine option to do it, but earlier is typically better with these planned applications. So when is it taken up? This is a good graph you can kind of visualize in terms of peak demand, really right around here. So we're seeing peak demand of nitrogen occur between about V10 and tasseling within your corn plants. So if we look at when we need the majority of our fertilizer available, that's about the key point in time. Once we get beyond about that VT, that R1, where we start seeing the ear development, in many cases, if you start looking at going out and sampling your soils, looking at the nitrogen that might still be there from fertilizer, we see really essentially the soils being completely depleted but nitrate at that point in time. And it's because we're getting a situation where that crop is actively growing, it's scavenging as much as possible. So when it comes down to overall nitrogen requirement, we know essentially this is the period where that crop is scavenging, and that's really the key points in time when many of our yield potentials are being developed, and we really want to try to maximize that as much as possible to get the most efficient use of the fertilizer we're applying on an annual basis. The thing though, when it comes down to a lot of this, it'd be really a lot easier if we could predict the weather. And that's really kind of the key with a lot of this is, I mean, a lot of these best management practices really are just keyed in on essentially normal conditions. And that's really the thing that becomes issue with nitrate, is that when it comes down to loss, is that it's really dependent on the amount of rainfall we get on an annual basis. And you know, when we start talking about things, I mean, really the biggest elephant in the room becomes rate when it comes down to this, when it comes to loss. So I'm going to spend a little time talking about that, how we develop that, and why, and kind of where we're looking at, you know, moving forward, what we see in terms of overall trends with some of the rates that we're seeing across the areas within the different BMP regions. So Brad covered this earlier, but once we know that essentially a lot of our issues really boil down to, if we start talking about total loss, it's really dependent on two factors. It's dependent on the concentration, but also the total amount of water we have flowing within or across our landscape that affects the total load that's being lost. So a lot of what we can do, while we can reduce the concentration as much as possible, we still have some challenges here, particularly when we get these, we see weather patterns with more rainfall occurring at key points in time where we tend to see a greater risk for loss. What we're doing though right now really with it is a lot of the focus on the guidelines is in what we call this maximum return to nitrogen approach. And I think there's a little bit of a misnomer too, and I'll talk about that, is that while this approach focuses on economics, we have a lot of data. If we start talking about the environmental and the economic, what's most economical is they tend to go very well together. So overall, when we start talking about environmental issues, it's really hard to look at that on every field that we're running a test, but I'll show you some of the things we're looking at. Is that we do know that essentially these two go very well hand in hand in terms of reducing the risk. If we can hit the optimal rate within a given field of reducing the risk for nitrate loss on an annual basis. So you'll hear MRTN a lot of times, or you'll hear EONR. It's kind of, use them interchangeably, but the maximum return to nitrogen approach was really looking at trying to be more consistent across state lines and how we recommend nitrogen. And I know that's a lot of times, especially if you're near a state boundary, you start looking at some of the recommendations and the changes that come across state line. It doesn't make a whole lot of sense because your soils tend to be the same, whether or not you're on one side versus the other. But the thought here, though, was to start looking at a few issues that was occurring. This was back in the early 2000s when nitrogen prices were starting to spike because of some of the increases in natural gas prices, is how do we make adjustments to that, or should we be making adjustments based on the price of commercial nitrogen fertilizer for what we're recommending for corn? So if you look at it, it is a cross-state program, but the states do tend to maintain their own recommendations. And that is a challenge, I know, for some of you that live near borders. If you start looking at some of the differences and you start seeing some of why it's one thing's recommended versus the other, doesn't make a lot of sense. But when we've looked at combining the data always hasn't combined very well in terms of making sense across it, just because of where some of that data is being generated. So initially, a lot of the studies, we looked at analysis of long-term studies dating back to '79. The database right now, I have nothing earlier than 2000, and I'll talk about that, because I know there's always a lot of criticism about older data in the data set. And what I do when I start looking at our recommendations, I do an evaluation of some of the older data as I'm making updates to it to see if it changes anything with or without some of that data in there. In most of the cases, the older data that's left in there, it doesn't really change anything what the recommendation is, so we just tend to leave it in because the more data, the better when it comes to some of these approaches. So these have been a combination of on-farm, if we start talking about what we use for our current database, and small plot studies across the region. And really the key, again, is to get a lot of locations across the different areas to get a good estimate of the optimum N rate. So there is a tool available online for this. I do have, our publication also has the recommendations that are based on this, but realize that if you go to the University Extension website, look at my rate table, I do a little rounding that's within about a pound or two of what the recommendation is from these from this rate calculator. It's this cornnratecalc.org is the website, but if you just would Google corn N rate calculator, you'll find it. And I'll kind of talk a little bit about where our recommendations are just here before the end with some of the recent updates. Currently in Minnesota, we have 184 corn following soybean sites and 73 corn following corn. And I've been, one of the advantages of having Fabian Fernandez here at the university is that I've got more people now working on it. where we can add more locations in, because I'd like to have 2-3 times the number of sites to be able to have more data, because more data is better with this. But again, this is a regional approach that's been doing. There's a few states, actually Indiana isn't up there, but that actually is actually in the, but it's in the calculator now. So what does the calculator do? Well, the calculator takes a database. So it takes all the sites we have in there. We have nitrogen response trials. It takes the response to nitrogen from each of those trials, and it looks at them all to generate essentially a recommended rate for a particular region or a particular state. You can play around a little bit with the data, but you can look at just some different graphs with it if you go online. This is just showing the optimum N rate versus optimal yield. I'll talk about that here in a moment, so you can kind of see essentially the individual sites within the data set. Where is that data coming from? You can also generate some graphs looking essentially at economic optimum rates among the sites. And the main thing here is really looking at these net return sites. So what the MRTN approach does is it looks at the price ratio of the cost per pound of N for commercial fertilizer to the value of the corn crop. And really, if you're starting to looking at planning purposes, what you'll generally do is to take what your targeted corn price is that you're looking at for your marketing side, and then comparing it with the current the current price of nitrogen. In many cases, if we start talking about price ratios, I generally use 40 cents a pound N or $4 corn, because that comes out to a 0.1 price ratio, which is typically pretty common. If we look at about 75% of the circumstances within the last 10 or 15 years, we've been within that 0.1 price ratio on that. So for planning purposes, most of the time I'll look at the 0.1, and a lot of times you'll see us present data, it'll all be at that 0.1 price ratio. What the calculator does is it says this is the cost per pound of N for increasing N rate. This is looking at your gross return to nitrogen, and this looks at what we call the marginal return. So essentially it's looking at the return for every pound of nitrogen you apply in terms of a dollar value. It's generating that, and it takes that coupled with this price of fertilizer, and it generates the MRTN value, or the maximum return to nitrogen value, in what we call the profitable range, which is plus or minus $1 for that MRTN. And really what this is in place is to really account for some of the uncertainty we have, because we know with any sort of calculation we have, when we're doing this calculation, there is some error involved within that. So there's some flexibility in there. It's typically plus or minus about 10 pounds from the MRTN. So we're not talking about a wide range there, but we do realize the fact that we aren't necessarily with one targeted point covering all circumstances, because you can see in this histogram, you can see kind of what the break is in terms of percentage of sites that would be kind of plus or minus that MRTN value. So the nice thing about this is it can change over time, and that's really been the big thing about nitrogen guidelines, is we want some flexibility to reflect current conditions, reflect current hybrids that are out there, to be able to make sure we're most accurate as much as possible with some of the current practices that are involved. So Brad showed this earlier, and this is one of the key things, because we get a lot of flack from this, especially with the MRTN, that we're only focusing on economics. And when we start talking about it, we do look at other things when it starts looking at environmental conditions, because one of the things about the MRTN is if we start talking about from a loss standpoint, if we could monetize that, you could build that in as another factor into that actual model and generate the recommendation if you knew how much it cost, and how much some of that loss in nitrogen cost. But overall, if we start talking about this, Brad was talking about this earlier, this is a situation, southeastern Minnesota. This is looking at residual soil nitrate in the top 5 foot of the soil profile, and that's what we typically look at with many of our studies to look at risk. So what we know, that if the nitrate's there, there's no crop there, that we are in a situation where that nitrate can be potentially lost. So in many of the nitrogen studies, we measure residual nitrate to give us some indication essentially of how much nitrogen, or how much that might be there and we potentially lost, just based on where we're at compared to our economic optimum N rate, which in this case is somewhere between 90 and 120 pounds. And if you look at it essentially in terms of the overall target, if we look at the general increase in residual nitrate, is that up to the EONR, whatever that point that is, whatever number that is, we know that in general that risk for loss is potentially low. We don't increase our residual nitrate much until we get beyond that economic optimum nitrogen rate, when that crop has as much nitrogen as it can effectively utilize, where it can almost leave it pound for pound in the field post-harvest because it isn't effectively using it. So whether or not the economic optimum nitrogen rate's 100, it's 150, it's 200, this relationship's always the same. So if you look at an individual field, it's more about targeting the optimal rate for a particular field than under-applying, because we know that in general, that under-application, we're not really gaining all that much in terms of or anything at all when it comes to potential reductions for nitrate loss to the water. So really, that's really been the key, is trying to get as close as we can to possible, which is some challenges, which I'll talk about here in a moment. So where are our trends? These are just looking at trends in our economic optimum nitrogen rate, or that MRTN value over time. These are just yearly averages where I've summarized back to 1990 through, this is through 2021. I've got a newer version of this, but the trends are pretty much following the same patterns. Where if we look at in general in the continuous corn databases, at about 2000, we started to see it's a general increasing upward trend in the average MRTN rate on an average basis. And what I really attribute this to is really our changes in some of our hybrid genetics, particularly as we started to get into situations with more rootworm or more this BT tolerant corn, more residue. And one thing that we know, the difference between our corn recs and our corn soybean recommendations is that main difference in why we recommend more nitrogen for continuous corn really is that immobilization, or the fact that the residue has a lot of carbon, it needs nitrogen to decompose, and it ties up some of the nitrogen that's in the soil that's being applied either in fertilizer or that's being mineralized through the organic matter itself. So when we start looking at the more residue we have on the landscape, it makes sense essentially that over time with increasing residue that we're going to see increasing trends. But if you look at starting at around 2020 or so, seeing that these averages that we kind of peaked here, this is around 2018, kind of as we started to get to the end of some of that wet period, and it started to go down as we've seen some of these dry weather conditions. And that's one of the things I kind of track. If you look at, in general, the average MRTN increases with adding the database in, we haven't really been seeing that much of an effect on the rate recommendations. With more of the recent, it's been more flat with continuous corn. Big increase from about 2000, but it's been more flat for the last 4 or 5 years. With corn soybean, what we see relatively flat till about 2014, then a jump. I mean, really these bars represent the number of sites that we added to the database. This is the time that Fabian started. So more people doing research, more data. Saw a slight increase in terms of the MRTN, but it's been more consistent over time. And that's been one of the general trends that we've seen. While it's creeped up a few pounds here and there with the recommendations for corn following soybeans, that overall the number's been relatively constant compared to continuous corn. So what about different areas of the state? I have looked at this. I mean, I've looked at, particularly in the southeast, some of these lust soils, these deeper soils, we do tend to see a tendency for higher mineralization potential. And when I've looked at the data set, the corn soybean data, we see, maybe around a 10 to 13 pound difference in terms of the optimal N rate in the southeast versus the south central. If you look at the continuous corn data, though, it's exactly the same. And that's been one of the things that I've tried to do, is to look at differences in these areas to see if we could fine tune our recommendations. This is just based on parent material, but overall there just hasn't been anything consistent enough where the difference is big enough where we see that big of a gain. I would say for most people, if we look at that profitable range, if they look at south central Minnesota versus southeast Minnesota, southeast you might be midpoint to low or to that lower end, that minus $1 on the profitable range for corn soybean. But if you look at south central, those regions, the southwest, you'd be looking at kind of that MRTN to about plus $1, because those tend to be sites that seemingly need a little bit more nitrogen just because of denitrification potentials. But it hasn't really sorted out consistently enough where I can make the change. So you look at, like in the BMP publications, there's really no talk about any particular changes, just because right now we do not have the evidence for that. So a lot of people talk about increasing yields. Why don't we need more nitrogen? Well, we just don't have the data for that. If you look at, these bottom graphs, economic optimum nitrogen rate, this is at the 0.1 price ratio versus grain yield at the EONR. We see some trend in terms of an increase, but if you look at a lot of these trends, what you really want to focus on, this is what we call this R squared, or this correlation coefficient value, and that the lower this is, what this value talks about is the amount of variation In this grain yield, that can be predicted by variation in economic optimum nitrogen rate. In general, we're talking only about 10% or less of that variation. So the overall trends, while there might seem to be something there, the general predictability of one versus the other really isn't there. And it's one of the things I like to point out with some of this data within the database. We just look at this 250 bushel per acre yield line. I've got situations where I've been able to get 250 bushels max yield with 30 pounds of nitrogen. There's been some circumstances where we've needed 300. It's just sites that need more nitrogen. And that's been kind of the key on a lot of this, is that trying to decouple this thought as we increase our yield potential, that it isn't necessarily that we're going to need more nitrogen just because of that increased yield potential. And one of the things that we've seen consistently, particularly in corn production, is the fact that we're seeing lower protein in much of the grain. So if you start talking about the amount of nitrogen being taken up by the crop, even with these higher yielding crops, it isn't a whole lot different than we'd see now versus you may have seen 20 to 25 years ago. So, the question then is, how do we look at this? And I think that's one of the key things that we start talking about our current recommendation system, is that there isn't a lot of talk about how do we adjust from site to site. And that's been one of the things that we've looked at within a lot of our current research, is try to figure out how can we be more site specific on an annual basis. I mean, I have looked at a number of factors. Again, we know that maximum yield doesn't, if we look at just the ability of the site to produce nitrogen without any commercial fertilizer, there is a good relationship between that and our optimal yield level. So one of the things we talk a little bit about is, how do we fertilize these fields? Do we have high yielding areas of the field? Do we fertilize those with higher rates? Do they need higher rates versus the lower yields or the yielding areas, or vice versa? And what we tend to see, essentially, the sites that need a higher optimal nitrogen rate tend to be those sites that are going to, that the soil themselves can't supply as much nitrogen. Yet there's really no easy way to predict this, and that's really been the challenge with that. Because if I knew that in terms of the overall supplying power of most of the soils, that's where kind of crop models might come into play. We might be able to be more specific in terms of being able to hit that, be closer to that optimal nitrogen rate, which is really the target, as much as possible. So this is just taking that data set, looking at what the difference is between sites where the soil supplies less than 50% of the total N versus greater than 50% of the total N. You see a difference in the optimal nitrogen rate by about 60 pounds. So in terms of looking at different options, I mean, this is one of the things I'm looking at right now, whether or not we can actually get a general handle on what that soil supply might be, because if that's the case, then I think I could use this data set more effectively in terms of better targeting what your optimal nitrogen rate will be on an annual basis. So some of those trends, I mean, if we see those increasing trends, does it mean we're getting more nitrate moving downward? We really don't have the evidence for that, because again, a lot of the data we're measuring, we look at some of the residual levels, we know there's a greater risk. But that's the problem with nitrate. I mean, there's many, if you look at the nitrogen cycle, there's many different ways it can disappear within that cycle. So measuring that gets to be somewhat problematic. And that's really what's really difficult about nitrogen versus other nutrients like phosphorus and potassium, is that if we don't have the mobility, especially with P and K, it's a lot easier to assess things, especially with a soil test, to try to figure out what our risk is in terms of needing additional fertilizer to maximize yields on those given field. So I talked about the lower part of that. So what about soil tests? Are there some options right now? That's one of the things that I do a lot of work with is soil testing. Minnesota has maintained an option for a deeper nitrate test to look at assessing potential carryover of nitrate nitrogen from one year to the next. It hasn't been anything we've pushed in the southeast, mainly because we know that nitrate's more transient in many of these soils, just because of we can move relatively quicker, especially if we start talking about soils that have less clay in them, where that tends to slow down some of the water movement. So there is an option, though. I mean, the issue, though, is really boiling down to whether or not you think you have residual. And really, we break this down looking at this flow chart, looking at different crop species preceding corn, whether it's manured or not. In these yeses are situations where the nitrate test might have some value to start looking at the relative potential for situations where you may have a field that needs less commercial fertilizer nitrogen as a starting point, just because of some potential carried over nitrogen. So corn following soybean manured situations, corn following corn manured, are situations where we have low precipitation, where we may have some of that nitrate that's being carried over from one year to the next. For the most part, like a corn following soybean situation without manure, even at a dry condition, what we tend to see with soybean is a net utilizer of nitrogen, that the amount of nitrate in the profile isn't necessarily that fluctuating from one year to the next. I mean, I have looked at this with the 2-foot N test with applied nitrogen, and these are both south central and southeastern locations, that there is some relationship if you look at it utilizing the amount of N in that 2-foot test of nitrate with the overall nitrogen requirement. We did put this into the field location, a few field locations a few years back, but had some pretty mixed ability to be able to utilize some of this to be able to adjust some of our nitrogen rates within and across some of the larger fields that we're looking at within that particular project. One example, though, that I want to bring up, though, when it starts talking about some of these residual N tests is this situation. This is a field site we had by St. Charles back in 2021, a situation with manure history and also with cover crop history. We start talking about, I'll show the data with the residual nitrates, a 27 part per million residual nitrate in a 2-foot depth in the spring. Right now, when we equate that back, is roughly about 180 pounds of residual N credit. So that's a pretty significant credit within that particular field. The top line here is response to, this is 6 rates of nitrogen, where the 0 yielded as much as the 250 pound of spring N rate as urea. So this is a situation where that test may have at least helped to say, well, we may not need to put as much nitrogen down initially in the spring. It's kind of amazing looking at this. We took the test both in the spring and the fall, and while there is some change within that 2-foot test, it wasn't all that much. It was always above that 25 ppm, which is a pretty high N credit within many of our locations. So there may be some options for this moving forward. It's not anything you'll likely see probably, though, in some of these changes to the BMPs, but it might be something to consider if you've got a heavy manure history, if you're looking at whether or not you might be on that lower or higher N responsive scale. This is just looking at the recommendations. We give credits for different ranges in part per million values for that 2-foot test. The current one only goes up to 18 part per million, but I've actually extrapolated this out to over 25 part per million, because at 18 part per million with our older recommendations, that was the maximum recommendation for continuous corn through the early 2000s. So there was really no need to go any higher than that. Now, since I've got situations where we can get higher than that, I've extrapolated this out. You can kind of see how we utilize this. Why we utilize this system is the fact that the MRTN approach, if you're going to utilize something like that, assumes some sort of residual nitrate in your profile on an annual basis. And even in the Southeast, many of our locations, it's not uncommon to find about 40 to 50 pounds in the top 2 feet of the soil profile of nitrate nitrogen in the spring. So we're going to be carrying some of that over, and a lot of that comes back to what Brad was talking before, is that we have nitrogen being mineralized constantly, and if there's no crop out there, there's going to be nothing that can take that up, and you'll see you can see a certain amount that's maintained in the soil over a period of time. What other options if you're looking at adjustments? Tissue tests. Right now I do see some people ask about in-season tests, particularly if we talk about leaf tests. The interesting thing, if we look at Southeast versus other areas of the state, it's not uncommon for me to see differences in terms of what I would deem to be an appropriate or an optimal concentration, say, of nitrogen or potassium or some of these other nutrients based on location. Some of the other options that have been out there are like the basal stalk N test. The problem with a lot of these tests, though, they're post-mortem tests. So essentially they're not tests that we can utilize to make decisions up front. So we're looking at how our management, how that was with, it's more of a report card of management within a given year, and then hopefully if you have enough report cards, you can make adjustments over time. But that's been kind of the challenge, is how do we make adjustments the given year that that crop is actually growing. Some other options, this is just a supplemental nitrogen worksheet. This is kind of what I call a qualitative approach. It essentially assesses whether or not we think there's a potential for nitrogen loss. The problem with a lot of this, though, it doesn't give a lot of guidance on the rate that you apply. It just gives a set rate, and hopefully that's going to be enough to maximize yield based on loss. So in terms of options, we have pretty limited options. And I'm not going to talk about stuff like drones and sensors, because we go back to that curve and we start talking about nitrogen uptake, that in many cases when we're sensing most of these fields, it's at points in time where we don't need a lot of nitrogen and that crop isn't really visibly showing any deficiencies that may be relative to what we see at the end of the year. So again, the fate of nitrogen is difficult to predict, so that's where it becomes kind of problematic. So a lot of these best management practices, really they're practices, again, that should affect or should limit the loss in normal years. This is the one that's kind of been coming out more, and I kind of like the analogy of the can of worms, because it is kind of can of worms, to start talking about some of these biological products that are out there. And a lot of you that are farming, it's just amazing to me the number of different ads that you see in terms of these products, and a lot of questions of whether or not they're worth it in the end, whether or not, because really what these products are doing is they're supplementing the bacteria or some of the bacteria that might already be in the soil, trying to really kickstart those to supply inorganic nitrogen to the crop itself. I did include a handout, and it wasn't there when you came in. I've got two handouts up here. One of them is on some of the summary of the biologicals that we have. There was a summary put out a couple of years ago of some of these asymbiotic end fixers. Most of those products, essentially, they're asymbiotic, so they're bacteria that will grow with the crop that are not supposed to have negative impacts on the crop itself. And many of these, again, are bacteria that are already in the soil. They're just trying to get them to work better. Most of our data, though, would say right now, there isn't really much of any positive data that they're actually doing what they're saying they're doing and can reduce the overall N rate. They become, to me, a little bit more of a sleeping pill for some people if they're looking at reducing rates, to try to have something to use that where they feel better about some of those rate reductions. And if they're getting the same yield with the product, they're happy that essentially because you get that potential reduction in what might be happening to that nitrogen if it's not being effectively used. One thing do be aware of, there is a bill right now in the legislature, that a proposed bill to look at paying or comping the cost for some of these. Right now, though, again, on my end, and you look at some of that data if you want that handout, is that we're not quite there with these things. They're not consistent enough across locations where we can really expect them to work even 50% of the time. I'm thinking it's 1% or less of the time that we see some benefits a lot of these products, and a lot of that has to do with there's a lot of issues in terms of the handling of these. So just going to wrap up here before we take some questions. You have to remember, though, that when it comes to these best management practices, a lot of these things are focused around these 4R system, and that's what Fabian's going to be talking about after lunch. A lot of the 4R research we're doing right now and what we're seeing in terms of benefits from some of these different practices, and that these things are an integrating system. I talk about rate a lot, but when we start talking about it, rate isn't the only answer to this. I mean, we aren't going to manage our way out of this by just focusing on rate alone. That's where source timing, placement, all these things become highly important, because they're an integrating system moving forward. And if you change one factor, I mean, you have to be looking at essentially the other factors to make sure that you're getting as optimal conditions as you can in terms of preventing loss, because we start looking at these things again that they are an integrating system. So again, I just want to give an update or a brief overview of what's going on. Well, after lunch, Fabian will talk about more of the research, because that's really the key when it comes to these BMPs as we move forward, is making sure that we're incorporating the current research as much as possible to make sure our recommendations are doing what we want to do in terms of mitigating both some of the environmental loss, but also trying to maximize productivity. So we got time for questions, Brad? Yes.
I know several years ago there was companies that were developing these nitrogen modeling tools. I think of like Thomas Operation, or then Adapt, and Pioneer had one as well. And they were all available on the market for a few years, and then they were all gone. Did they not work, or where are we at?
Well, I don't think they're making enough money for them is the problem. That's kind of with a lot of this technology. If you got a company that's developing it, even if we show some value, if they don't make money, they tend to jettison them. So that, I mean, in terms of the models, there's some advantages there. I mean, the issue with the nitrogen cycle, that you're modeling so many things, there's a lot of error that goes into it. So I kind of wonder, but the thing that, well, it would be nice to see some of those come back on. The question is, though, is how much do people trust if it tells them to apply less on that? And then with some of the things that we're looking at, particularly with less up front, is do we have some other option where we can look at in season, trying to make sure that we have enough at those points in time that we're not undercutting ourselves as much as possible. And I think the models themselves, if they are, especially with the AI, we have things that are going on with a lot of these initiatives. I think there's some potential there. It'd be nice to bring them back on, but I think that's really where a lot of it was. It just disappeared because they weren't making enough off of it to really stick with some of that. And it's kind of unfortunate because I think, again, that's probably looking at a lot of this, if you can get some accurate model with a lot of data in there to predict what, moving forward, what's going to happen, that's really what's needed with that.
Okay, well, along with that, have you done much research on do this aerial photography and looking for MBBI area?
Yeah, NDVI and NDREs, yeah. So Dr. Yushin Mao, he's at the university. He's actually working on some of that right now. What it boils down to, though, is the fact that in many cases, if we're trying to go early in the season, like NDVI measures biomass or green biomass in the field. So there's kind of an optimal window to do that. And in many cases, we start talking about scanning, it's really better to wait later in the season. So because you start to get more predictable in terms of what you're seeing for right now, what's going to happen later on in the growing season as that crop starts to hit points of stress. So that's been the challenge where I've seen, and I've done this, I was messing around with this probably back around 2014 before Yushin started. And it's hard to see some of those differences with that because a lot of times, they're picking up wavelengths that are visible wavelengths, so kind of what you can see. So if you can't visibly see it with your eye, you may not be, these things still may not be able to pick it up. The other problem with it is if it's yellow, what's that yellow from? So that's the other problem, is you need to be sure that what you're looking at essentially is nitrogen versus sulfur, which is yellow. Potassium causes yellowing. If it's wet and saturated, that can cause yellowing too. It's how do you differentiate between these issues? So there are some things that I think with the update of the BMPs, we'll probably talk about some of these things and where we're at with them because they aren't in that publication right now. And it's just the fact you haven't seen us promoting it much is that there's still some questions on some of that. You can measure it, but again, there's some interpretation that's involved, and that's really where the science is still a little bit lacking. So, good question though. Yes.
Cool. The point of view you're taking all the time is about the corn plant or the maximum return. If you change that point of view, the water, I'm looking at your St. Barrel data, residual at 0.7 parts for the 180 pounds per acre residual. How can we get cleaner water?
See, that's a good question, and that's where where we have issues, because it would be nice essentially if we could measure some of the water and what's in it on every field, and we can't. It's just not feasible with some of the technology we have. I think the main thing is just looking at trying to find situations where one like that one, that situation essentially what I would be looking at for a grower in that is maybe a little bit of starter and then coming back. Because what I'm interested in, Fabian might mention it, is what we call the pre-sidedress nitrate test, which is something we haven't necessarily recommended. It's got some limitations, some issues, but it's a follow-up strategy that we could use essentially for growers to potentially apply less up front. Because that's really the key with nitrogen is that you make the decision, you put it on, and if it isn't needed or there's nothing out there to take it up, it's just going to sit there. That's really the only way to get it out of the profile itself. It's then how do we make those assessments, whether it's something that we talked about like the remote sensing, which in that case there's so much there. It's just going to be green, you'd never really see any difference there. How do we flag those sites? And that's really where I've kind of been looking at on this, is what information do we have right now, or some tools that we can use, because it is pretty limited right now. So I think that's really the main thing, is to essentially pick out these sites, because what I said before, it's really more important to target the optimal rate, whatever that is, as much as possible. And if we can hone in on that better, that's really what we need to be looking at doing. But it's still right now, the technology, we can get plus or minus this few, maybe 10, 15, 20, it's probably even more than that from that optimal nitrogen rate on an annual basis. So that's where the difficulty lies right now.
I live near St. Charles. My well in December had 14 parts per million nitrate. 2 weeks ago, it had 15.9 parts per million nitrate. It was a 400-foot deep well. Is that the effect of the drought? And we had a 20 22, 23 drought reduced yield, is that the residual moving through?
Well, I can't talk to that in terms of, I don't know what's going on underneath, but certainly I think that's one of the challenges because we see that in the rivers. I mean, essentially, if you look at, it's at 88, 89, and you look at the river flow, and after that, when the rain started to come in, that there likely was some residual nitrate left over with that. So that's kind of where, there's been more interest in some of those deeper end tests in areas of the state for people to look at residual past those years. I don't know how much they use it though. And that's kind of the thing, that it's really getting trust in these things to make sure these numbers that are accurate is really the key with a lot of this. And I think it's getting growers trust in that. And I think, looking at more on-farm studies where we have some of these things working with growers, kind of like what's going on here already with some of the rate research, I think will be kind of key moving forward. But I mean, that's kind of the big thing, is you don't know. And certainly the risk is higher for residual nitrate, that if you keep applying the same rate, that there may be some carrying forward that's going to be picked up at some point. Because again, it's more applying the right rate versus, then we really want to try to avoid over applying as much as possible. But, figuring out what that right rate is really the issue.
It's pretty clear we're going to need alternative crops, cover crops, those kinds of things.
Well, there's some cover crops. So if you see that like in our BMPs, they aren't covered right now. Right now in the BMPs, that's mainly because when I started, there wasn't a lot of research on it. Now we have a lot of research. So that's, I think, going to be the big change, is incorporating some of this stuff in there and kind of what we know with the research. So
Probably over the last 50 years, and tens of millions of dollars spent on nitrogen research. And if you look at some of your graphs, 1 year to 30 comp acquired, next year is a heart per comp. We don't know what to put on. And your own data, you show a lot of stuff, years have shown that a wide range of nitrogen requirements with no understanding why.
And I think that continuous corn was the common up front too, as some of that carried over. As we get these dry years, it makes sense that it goes down. It is. That's the problem is, if I knew better on the weather side, I could tell you about how much maybe to start with up front and then make some adjustments in season if it gets to the point where we need it. And that's kind of the issue with nitrogen. With P and K, it's easier, because if you don't utilize it, as long as it stays there in the soil, as long as there's nothing that'll wash it out of the soil, you'll pick it up at the soil test and you can use that maybe and make adjustments to the season. It isn't the case with nitrate as much as issue. And that's said why, we invest all this money in it, and people ask, why do we need more nitrogen rate studies? It's just mainly because I think as we move forward, especially if we're using AI for it, it's just having more information, more scenarios, having as much information as possible to try to fine tune things is really what we need. So that's always the question, is do we need more, and my answer to that is we need about as much as we can with as many scenarios as we can to fine tune this more, because nitrogen, it'll keep you employed for a while trying to figure that one out in terms of trying to fine tune recommendations. One more?
Well, Dan, your answer there. More data, we possibly back to your recommendation. Ferret out possibly some differences within the region that you spoke to earlier. And then Brad or Warren brought up vulnerabilities of that. You guys feel moving forward you're going to have enough of research or funding to do the research in the vulnerable areas that maybe you can ferret out from the fiction?
I don't know if it's as much funding, it's time and people. And that's where a lot of it is. And I guess that does boil down to funding, is really doing a lot of this, because, there's been some targeted approaches by the Department of Ag to put, areas from nitrogen rate trials. I've been working with some of these NMI level 2 sites for a number of years with that. But there's also been a focus on the Southeast, which is some rate trials just to try to get more information out of these areas. So, there is some being there. It's just essentially having the time and the coordination to do it is really the main thing, because I think that's kind of the challenge. This on-farm data, it seems easy, but it does take a fair amount of time to make sure you have good data, because I want to make sure we have good data, because you can go out and collect a lot of bad data and it's not going to be helpful with that. But that's kind of the thing, the big thing. You see Iowa doing that with their nitrogen initiative. They put a lot of money into that to look at a lot of research across the state. There's some advantages at least to that on the nitrogen side. It's just having the people in place to do it, because Minnesota is a pretty big state and there's a lot of variability across the state in terms of difference. And with our guidelines right now, really it's been pretty consistent across the state what I've seen with NREX on it. Obviously don't hit every circumstances. You get up into Red River Valley, things might be different. But if we had enough data in there, we could look at that and split some of these states out, we might see some differences but it's been pretty marginal at this point. But it's, again, I'm limited compared to what some of these other states are in terms of the amount of stuff they're generating. So, and a lot of it's time. I mean, time's the big thing. So.